We'll now discuss a popular class of ambiguity models being the multiple prior models. In the multiple prior models, people say, well, in ambiguity, we don't know precisely what the probability measure P on the state space S will be. So let us take a set of probability measures and we say the true one is one of them, but we don't know which. So that's how we specify our uncertainty about what the probability measure is and our ambiguity. And then we can specify all kind of decision models using that set. And I give some examples. For instance, a popular model is max-min expected utility. It was already written in statistics in 1950 by Wald, but Gabor-Schmeiter gave a decision foundation to it, and then it became popular in decision theory and economics. It says, well, we take a subjective utility function, as we always do, then we don't take one probability measure on the state space, but we take a whole set of probability measures, a set of priors on the state space, and then we proceed as follows. If we evaluate an act X, well, acts assigned to states of nature, maybe outcomes, or in Anskamp-Allman framework, in fact, probability distributions over prices that are evaluated by expected utility. All of that we assume being the case here. But then we go on as follows. For every element P, every probability measure on the state space contained in the set of priors, we calculate the expected utility of the act. So this is the expected utility taken over the state space. And then we take the infimum that we get over all those P's. That is the value of the act. Well, this is a bit of a pessimistic attitude, as you can understand, taking worst of all possible cases that you can think of. And often this is taken to reflect ambiguity aversion. And maybe I should repeat, we're assuming the Anskamp-Allman framework here with expected utility for risk, so that every deviation from expected utility then can be taken as an ambiguity attitude. So that's how it works. You can imagine the dual of this, max-max. You do what we did before, but you take the supremum, not the infimum. That model that is very optimistic. That can be taken as ambiguity seeking. But then you can also imagine that we use combinations of the two. So we take, again, utility function, we take this set of priors, but then we take a convex combination of the two above models. We take alpha times infimum plus 1 minus alpha times supremum, alpha a number between 0 and 1. Well, if we do such a thing, then as in all the multiple prior model, we can take the size of the set of priors is the degree of ambiguity. Of course, if there's a big set of possible probability measures, you don't know very well which it is. You have much uncertainty. So that is then often taken as a state of your information, the degree of ambiguity in your information. And then alpha is then an index of ambiguity aversion, pessimism maybe, but we take it as ambiguity aversion usually here, because the bigger alpha is, the more attention you pay to the bad side of the story. So that's how this model works. Well, there are pros and cons to multiple priors. One pro is that sets of prior fit well with natural language, way of speaking. Often we must specify quantities. Maybe we say, oh, that probability is between 0.3 and 0.4. That probability is between 0.6 and 0.8. It's a natural way of speaking. And therefore, this multiple prior model connects easily with that. So that is one pro. And related to that is easy to understand. Upon first inquiry, immediately you see, oh yeah, if I don't know the probability, maybe there's a whole set of possible probability. I don't know which it is. So you immediately see that that is a way to capture this intuition of ambiguity. For instance, with the rank-dependent model, you have to think more. One is more pessimist than the other. It's more complex mathematically. That also goes to the third point. For multiple priors, you need not develop new mathematical tools. You just expect utility calculation. You've seen that before. Taking infimums you've seen before. There are no mathematical tools that you didn't see before. For instance, in a rank-dependent model, you have to know how this rank-dependent integration goes, Schocker integral. You have to understand a bit of that before you can see how it can capture ambiguity. So in that sense, the rank-dependent model requires more advanced knowledge. So that's then a big pro of multiple prior. It adds to its popularity, of course. But there are also cons. One con is that the decision rules are quite crude. If you only look at the supremum and the infimum, you don't care at all what happened in between with the other probability measures. That's not a refined natural process. So in that sense, the decision rules are quite crude. Also, in full generality, the theory is too general, so to say. You may remember when I introduced rank-dependent utility and these non-additive weighting functions. I said non-additive weighting functions are too general. We need specific cases, less general sub-cases to obtain tractability. These things hold even more for multiple prior, because sets of multiple priors is of even higher cardinality than sets of non-additive weighting functions. So the theory is way too general, and we surely have to find special subcases before we can do business. A third problem, maybe related to the second, is the status of the set of priors. Is it endogenous or exogenous? Well, sets of priors and maybe sets of numbers are natural ways of speaking linguistically, but usually information from nature doesn't come as sets of priors in that form. So in that sense, if you want this multiple prior theory to be a general ambiguity theory, you will have to allow the set of priors to be endogenous, that it's a way for the decision maker to express beliefs and degree of ambiguity and the subjective these things are. However, this theory in that manner is way too general. People don't know how to handle it well. So I don't think I ever saw an experiment where the set of priors was derived from preference, unless the most simple case where there are only two states of nature. Okay, that's doable. That's doable in many theories. But the moment the theory shows that richness of three or more states, it's getting too intractable. And therefore, I think all the experiments I ever saw, the set of priors was not determined endogenously, but was exogenously determined by the experimenter. The experimenter would just say to the subjects, this probability between 0.3 and 0.4, that probability between 0.6 and 0.9. So they would just give the information to the subject in that form, which indeed is a natural way of speaking, but it's not the way information nature provides us information usually. So that's also a big problem in the multiple prior theory still. But if point two, if tractable families are developed, then the problem three can also be resolved. And there is work going on. For instance, epsilon contamination is a particular way of choosing sets of priors. That's generally a special case, and that's one popular case that people often work on. And work is going on this topic. There are generalizations of multiple prior models. For instance, there's the variational model introduced by these three people. It has a quite pretty preference axiomatization. It is quite like, let me already put up the formula. It's quite like max-min expected utility, but it introduces an additional thing, being a function small c, that to each probability measure in the set of priors assigns a real number. And there's a sort of a handicap that's given to a set of priors. You can, let me already show you one horrible handicap. For instance, if for some probability measure p, we let c be infinite, that's a horrible handicap. Then you know this p can never deliver the infamy. So this p doesn't play any role. So that way, by giving some probability measures a big value c, you take care that they have less chance to impact your decision. That way you can distinguish that some probability, maybe you find them more plausible, you give them a small handicap. The probability measure that you find less plausible, you give them a bigger handicap. So that way you can distinguish a bit between probability measures. That's exact degree of generality. So that's a nice special case. I'll present a popular special case of variation model in this slide, and that is what is called the robust model. That was introduced by Hansen and Sargent in the year 2001, and that model is a special case of variational model. It takes a particular C function. That C function is relative entropy. Well, here you're assuming that the particular probability capital Q is quite plausible, maybe the most plausible probability measure according to your belief. And for the other probability measures, you don't want to rule them completely out, but you give them handicaps relative to Q. Maybe the C value at Q is 0, so in that sense it doesn't have a handicap. And then the other functions, other probability measures, the farther they are remote from Q, the bigger the handicap. So you take a distance of a probability measure to Q, that is the handicap Cp that you give to it. And the distance that you take is the relative entropy. So relative entropy is a particular distance measure. I will not define it now, but that's something that you can do, and then the variational model becomes more tractable. So this is a popular model. Here I wrote, I already said, the slides have to be a bit verbose for this occasion. So this approach is popular in statistics, also in macroeconomics. People sometimes use the term model uncertainty to capture this. I think it's a bit of a misnomer, because model uncertainty is a general term in methodology of science. reflecting many kinds of very fundamental uncertainty. Here we are in a quite narrow domain. You only think that you have uncertainty about is the probability measure. That's ambiguity. So I find it a bit of a misnomer. But anyway, this term is often used for these models, and it adds to its popularity. And popularity we find in expert aggregation, climate change, for instance. Their ambiguity models, and also the ones that I presented, are popular. Well, I will turn now to other ambiguity models. That will be in next recordings.